Hello everyone, my name is Thanos. I work for Capital One and I will be talking today about MCL clustering of sparse graphs in Apache Spark. Let me start this presentation with a brief disclaimer. I'd like to say that Capital One is not an advocate of and does not necessarily encourage the use of any of the technologies, products, or projects mentioned in this presentation. Having said that, I'm going to introduce a little context about graphs and their applications. I'm pretty sure that most of you at some point have worked with graphs before. And we know that they can be used to many types of, to model many types of relationships and processes. In particular, sparse graphs are a special category of graphs, and what makes them different is that they have a very low number of edges compared to the maximal number of edges. Now, a graph that's maximally connected means that every node is connected to every other node. A sparse graph is one that each node is only connected to only a few other nodes, or maybe even none. Specific applications of sparse graphs can be social networks, like how many friends we have on Facebook, computer networks, biological networks, power lines, and citation networks in papers where one author can cite another author. The problem with graphs is that when we have a very high number of population in the graph, then a dense representation of the adjacency matrix. The adjacency matrix actually is a matrix that has information that where each node is connected to every other node. So if we want a dense representation of this matrix, then this will probably not fit into memory, and calculations using this matrix would not be practical. So that makes a sparse representation of the matrix a requirement. Now let's briefly talk about clustering. Now, clustering is an unsupervised method of machine learning. Unsupervised means that we don't actually have a ground truth of labeled data. We have some data, and we're trying to make the best sense of it based on what we have. Now, that data can already have certain characteristics called features, and we can also build on top of those and create new engineered features. And then use these features to kind of group data together into groups of data that have similar characteristics. Some of the most well-known clustering algorithms are k-means, highly connected subgraphs, spectral clustering, and the Markov clustering algorithm, which we will talk about today. This algorithm was introduced, I believe, in the 1990s. It's a paper that has been cited many, many times, and it sees a lot of applications, especially in biological networks. A brief example of what clustering looks like. This is some randomly generated data, and this is how k-means can cluster the data. K-means is probably the most well-known clustering algorithm. It has some advantages and disadvantages. The advantage is that it's fairly fast and simple to implement. The disadvantages are that it's really sensitive in the starting conditions, which means that every time we run it, we might get different results based on where initially the starting conditions for the centroids are. Another disadvantage is that we need to specify the number of clusters in advance. So this would make sense if we actually know our data and we have a good idea of what we're looking for. But if we just want to cluster the data together and we don't know how many groups we want to use, then that's probably something that will be a disadvantage. Looking at graphs, this is an example of how we cluster a graph. This is also a randomly generated graph, and this is clustering applied that does community detection within the graph. So it's going to tell us that which nodes are connected to each other. And then this is the same graph with 1,000 nodes, which, as we can see, it starts to look fairly complicated fast. So visualizing graphs with millions or billions of nodes is actually quite computationally intensive. Having said that, let's try and introduce via an intuitive example what is the Markov clustering algorithm and how it works. And the idea is based on random walks and graphs. So taking a look at this graph that we see here, if we visualize this graph as each node being a point, and let's say that a human is moving around between those points, then it's highly more likely to remain within a subset of nodes that are densely connected. So if we're just walking randomly in this graph, it's way more likely that if we are in a node on this side, we will probably remain on this side for a long time until we get here, and then the random move is to make the pass and then go to the other cluster. But we might spend a long time on this side. And the same can exist on the other side as well. So there is a process that by simulating random walks in the graph, we can discover where the flow gathers. And this can be a way of actually forming clusters. So the flow can be calculated using Markov chains. Let's start with a brief example of what are Markov chains. So let's say that we have two different situations, like it's sunny outside and it's rainy outside. So situation A, it's sunny outside. When it's sunny on a given day, then let's say that there's a 70% probability that tomorrow it's also going to be sunny, and a 30% probability that tomorrow it will be raining. On the opposite side, if it's raining today, there's a 60% probability that tomorrow it's going to be raining again, and there's a 40% probability that tomorrow it's going to be sunny. So this is a way of simulating the transition between the two states. Here we only have two states. One of them is being sunny and the other one is being rainy. This can be modeled by an array. And given the starting conditions that are, let's say that today is sunny, and we form that as a vector, multiplying that with the transition array, it's going to give us the probability of what's the state tomorrow, which will be 70% it's sunny and 30% that it's rainy. Then again, if we want to predict 2 days in advance, then we will multiply by that array twice. 3 days in advance, 3 times. Looking at this in the long term, if we do many multiplications, then the final array is going to look something like this, and it's going to converge. And every time we multiply it, it's not going to change, which means that if we want to do some long-term predictions, they're not going to be good. If we want to predict this way what the weather is going to be like in 6 months from now, or even a couple of days from now, we're not going to get good predictions. We're actually going to get something that looks like the average probability of being sunny or being raining. So, having introduced Markov chains, the intuition behind the Markov clustering algorithm for graphs is that by simulating flow, as we saw in that example before, the flow will be stronger within dense regions than across the sparse boundaries, which means that the flow is going to remain within these clusters. Now, what do we mean by generating flow? We actually simulate this effect by having an inflation operator which is responsible for strengthening strong currents and weakening the weak currents. This can be modeled using mathematical algebraic functions. So the first part that we do is we do an expansion. Expansion means we take the array and multiply it with itself. This will allow new flow to be generated and connect different regions of the graph. The second thing we want to do is we are going to apply an inflation operation on that matrix. Inflation operation means we're going to raise it to a non-negative power, and followed by normalization, because we always want this matrix is representing the probabilities of moving from one node to other nodes. So we want the sum of these probabilities to be 1. That's why we're doing normalization. So this will strengthen the strong currents and weaken the weak currents. And then we do a prune operation, which means that for values below a certain threshold, we eliminate them. This process can be modeled by a simple flow chart, whereas given a graph, we add some self-loops, like the probability of a node returning to itself. We normalize by the column, and then we just do an expansion and an inflation, followed by normalization, pruning, and normalization. And we keep doing that until the matrix converges. Converges means that it does not change anymore. So then, by looking at the converged matrix, we can extract the clusters, and the clusters will form solid lines on that matrix. So, How do we actually implement this in Apache Spark? I believe that a lot of you might have used Apache Spark before. It's a framework for processing big data. It's a really popular framework. It was also mentioned yesterday in the workshops. And there are many machine learning libraries that can be ported in Apache Spark, and there's even Spark ML lib. So to implement this kind of algorithm in Spark, basically we need these operations. We need support for these operations. We need to do matrix multiplication. We need to be able to raise a matrix to a power point-wise, which means take every point and raise it to a power. And then we want to do matrix column normalization, which means take all the values in a column and divide by the max. That's like one way of doing normalization. And from all of those, the biggest challenge is matrix multiplication. And why it is because we want to use sparse matrices. And from what the last time I checked, Spark does not support sparse matrix multiplication for distributed matrices. So this proved to be the biggest challenge. A little more information about Spark. In case some of you have worked with Spark before, these are the distributed matrices that Spark supports. So a little more context about Spark. Spark is a distributed computing framework, which means that it runs on a cluster and it can scale horizontally, which horizontally means that if we want to add more computational power, we just add more nodes. So all of these nodes, they work together to process the data given to them. Regarding the kinds of matrices that Spark supports are row matrix and index row matrix. It's the coordinate matrix, and then there's the block matrix. We're going to introduce some of those briefly, but for now, let's focus on the coordinated matrix and the block matrix. The coordinated matrix is sparse by default, but the problem is how it's actually formed, which is not really convenient for doing matrix multiplication. The block matrix can be comprised of matrix blocks, and those can either be sparse or not sparse. The block matrix does support multiplication operation. The problem is that if it's comprised of sparse matrix blocks, then it's going to convert them to the dense representations before doing the multiplications, which we don't want. So let's briefly talk about what are the sparse matrix representations in general. So there's two categories, and these are some of the representative of each. The first one is those that support efficient modification. So the simplest way of storing a sparse matrix would be we have a list, and we just put in values of we have that element in that row and that column. Whatever is not included in the list is just zeros. So we can say that for this matrix that we have down there as an example, that the element on row 1 and column 0 is a 2. And then the element on row 1 and column 1 is a 9. And this way we just store these elements. When we want to add some new, we just add values to the list. When we want to delete an element, we just delete that value from the list. Anything not included in the list is assumed to be 0. So this is a very easy to understand method of storing sparse matrices. And it's also the number of values, the number of data that we need to store the matrix directly proportional to how many elements we have. Usually it's just 3 values for each element. And these would be like 4 or 8 bytes each, depending on what kind of data it is. The problem with this is that it's not really efficient to do any matrix operations with this kind of representation. So another representation is the compressed sparse row and compressed sparse column representations, which break the matrix into a number of other matrices that have all the information that we need, and they support efficient multiplication, especially when we're doing matrix to vector multiplication. So having said that, a naive implementation of doing the sparse matrix multiplication in Apache Spark would use a coordinated matrix, which is the simple coordinated list representation. So there is a way of doing that just by using functions out of the box, but the problem is that it's fairly slow. And especially when we scale our data, then we're probably going to very quickly, as we will see, hit the limit where it's no longer feasible to do that, because I believe a lot of people must have seen the Spark out of memory errors that we get when we try to exceed allocation. So an alternative implementation that we experimented on, it basically allows for the implementation of multiplication of Spark blocks without converting them to their dense representation. So, being able to do that will allow us to do kind of the same behind-the-scenes multiplication process that happens for dense matrices, but without converting them to dense, and having that being able to work with sparse matrices. So for this kind of approach, the most important hyperparameter is the block size. Like how large is going to be the block compared to the whole array. If the block size is very large, then multiplying two blocks together is going to result in out-of-memory errors. On the other side, if the block size is too small, then there's going to be too many multiplications to happen. There's going to be too many blocks, and we need to multiply these with each other. So in that case, there's going to be a huge number of operations. There's going to be a lot of shuffle, and it's probably never going to end. So the block size is a very sensitive hyperparameter on this approach, and it needs to be tuned. It needs to be tuned taking into account the actual data. So a few examples. To test this methodology, we generated some graphs from protein networks. Protein networks are usually very sparse graphs. To do that, so for those that have like a background in biology and genomic sequencing, they would probably understand that better. We took a couple of proteins, and then we found the similarities to each other. Like basically, we compared all versus all, and then we built a graph. And that graph has every protein in it, and it says it can find how closely the protein resembles another protein. So this graph has 15.3 million vertices and 318 million edges. It's an extremely sparse graph. So the density is 1.35 in the power of 10 in minus 6. Executing that graph, executing the Markov clustering algorithm for that graph, these are the execution times that we got on the left, and this is the total for each iteration up to the point where it converged. Most of the time it converged around the 25th iteration, meaning that the array would no longer change, so we could pull our clusters out. And this is the total time that we see for each approach. The naive approach is the one that uses the coordinated matrix, and as we can see, it's significantly slower. And then different block sizes can give us different results. The best result we get with a block size of 0.8 million. Now, again, we are creating a more dense graph this time using the same proteins, but we increase the sensitivity, which means now more connections are going to be captured that before they were pruned because they were too weak. So now we got, again, 15.3 million vertices and 616 million edges. Density goes up to 2.63. Here we can see that it's no longer possible to run the naive. It would crash. And also, it was no longer possible to run the block size of 0.8. The only solution that worked here is the block of 0.5. So the takeaway here is that, yes, the naive solution was probably not going to work for large data sets, but also setting the block size in the wrong value, this also is not going to work. And for the final experiment, we increased again the sensitivity, and we got a graph with a density of 3.82 multiplied by 10 in the power of minus 6. And here, a block size of 0.4 and 0.5 were both successful, and the 0.5 got us the best time. Conclusions are that it's still a challenge to do advanced matrix operations in Spark, especially doing like a lot of computation in Spark can be challenging. To be fair, Spark has a lot of built-in fault tolerance in it, so it's doing more work than a framework that would just do computation, and that gives Spark some fault tolerance, but it adds into overhead. I think that traditional HPC approaches would vastly outperform in this kind of situation, but then again, Using something like MPI and writing code in C would be way harder, and the implementation effort involved would be significant, and also there would be no fault tolerance. Spark might not be as fast as something as a custom solution like that, but it can work, as we can see, and it can fit very well into existing pipelines. Thank you, and I'm happy to answer any questions you might have.
Thank you so much. That's really exciting. Have you done any work with directed graphs or weighted graphs with this application?
No. So this is a bidirectional graph, which means that the connection from A to B, the connection from B to A might be different. So there might be a different value assigned on that weight. Yeah. But most of the applications tried have like a simple edge, which is only one value. But there is a way to make it work with like a bidirectional.
Thanks.
Thank you. Have you done any work with sort of these graph-based machine learning models in terms of performance? I know you mentioned it briefly toward the end, but in terms of performance with some of the more generic deep learning TensorFlow frameworks, how do these compare? Is there a compelling case for applying graph-based machine learning approaches for anything besides beyond protein research?
Yeah, good question. So this was mostly a big data application, which means that the data is so much that it would not fit into the memory of a GPU. So in that case, it would be completely different trying to do that in TensorFlow. Now I know that TensorFlow can do distributed computing, and to be honest, I don't know if it would perform better or worse than that, but it's definitely something that should be tried. Yeah. But generally, TensorFlow, from my understanding, is not being used as much for like this kind of big data applications, because the memory in these nodes that we're processing, this data was like hundreds of gigs. So we would have to resort to probably CPU solutions in TensorFlow. Yeah.
I guess who and how are the outputs being consumed? Are they being consumed in traditional visualization tools? Is it just CSVs? How does it work?
Depends on the requirement. So the output is, we have the clusters and the members of the clusters. So we have cluster 1 is this, and this. Cluster 2 is this, and this. The clusters are exclusive, which means that if a node is in one cluster, it's not going to be in another one. So depending on what we want, if we want to visualize, we could do any kind of visualization. We could just plot them, if it's plottable, if it's 2D, right? We could plot it and just put different colors.
Okay.
So it's almost the same as visualizing any kind of graph, I would say. If it's a part of a pipeline and then something else is going to work on it, then it's going to have to be inputted as a machine readable text file or binary file or something like that.